All right, so this is a fairly typical situation where a person has $500 sitting in their savings account. Now, as we have touched on briefly before, savings accounts don't pay a lot in interest. This particular savings account in this example is paying 0.1% interest each year. That is actually pretty high for current standard savings accounts. This would be a pretty good return as far as a savings account goes. Now, there's online savings accounts that'll pay you more, stuff like that. But for a standard savings account at your local bank, 0.1% is actually surprisingly high. With that in mind, if I just want to put that $500 in there and let it grow, how long will it take for it to double? All right, so that means we got to set it up, right? We got to set up our equation. And of course, I hope that you're going back and thinking about our compounding interest equation, A of t equals p times 1 plus r to the power of t. And when we do this, we got to start plugging in what we know. We start with 500, so that's going to be my p-value. And then it pays 0.1% interest. Now, this is where it gets tricky and where you potentially could have gotten caught off guard. We are not going to put 0.1 in for r. Because remember, that's 0.1%. And if I want to use a value for r in there, I have to turn that percent into a decimal. I know some of you are saying, but it has a decimal in it. Yes, it does have a decimal in it, but it's not a decimal. It is a percent. And so I still have to divide it by 100 to get it as a decimal. So that's going to be 0.001 when we actually plug it in here. Now, as you first wrote the equation, you might have thought, but that seems way too small. Yeah, well, it's only 0.1%. Don't expect big things here. And we don't know t, but we do know what a is. A is our final amount. Now, what amount are we trying to reach in this problem? 1,000, yeah. And notice it doesn't say 1,000, but it does say how long will it take for the value to double. So if it started at 500, it doubles. That means we're targeting 1,000. So then this is the equation that we're now solving. And so now we solve it using those techniques that we learned yesterday. So first thing you want to do, get the exponential part by itself. Now when I say the exponential part, I mean the number to the power of x or t or whatever it is. That means getting rid of the 500. So I'm going to divide both sides by 500. And when we do that, we have 2 equals 1.001 to the power of t. I'm solving for the exponent. What do I use to solve for an exponent? Logarithm, exactly. Remember, that's why logarithms exist, solely for the purpose of solving for exponents. So I rewrite it as a logarithm, and now it's not a regular base 10 logarithm, and so we need to go ahead and calculate it using the change of base formula. Make sure that when you do that, your base is on the bottom, so we're going to do log of 2 divided by log of 1.001. When you do that, you should get an answer here of about 693.5 years. Is this a good investment strategy? No. Especially if you consider that inflation actually averages like 3%. So in like 700 years, our $500 that's now 1,000 will probably buy a loaf of bread or something. It doesn't have the same buying power over time. And so savings accounts, they're a good place to keep your money. It keeps it secure, but you don't put money in a savings account to make money. Anything you get out of it, like that 0.1%, just consider it bonus. Just consider it gravy. It's better than nothing. But it's not going to be making you money there. It's just a secure place to keep it, and that's the key. So today we're looking at graphing equations that look like this. Now you'll notice what's different about this compared to stuff we've done before is that I have a number multiplied out front of my exponential. We haven't done that up to this point. We've added and subtracted in order to move the whole thing around, but we haven't multiplied it by something. All right, now let's think about parent functions and transformations then. Remember, the parent function is always just a number to the power of x. What number is to the power of x in this case?
2.
It's just the 2, yeah. And so your parent function is just y equals 2 to the power of x. Notice the 3 is not to the power of x. That's also why this is not the same as 6 to the power of x. Because the 2 is to the x, but the 3 isn't, so I can't combine those. All right, so then transformations. I'm multiplying this thing by 3. Well, the 3 is going to have the same effect that it has in all the other equations that we've worked with this year. Because we, earlier this year, graphed things like this. 3 times the absolute value of x. We also graphed like 3x squared. We've multiplied equations by 3 before. When we did that, you may recall that we described the 3's effect as a vertical stretch by a factor of 3. And that's what it is here as well. Multiplying by 3 is stretching it. Specifically, it's stretching it by a factor of 3. It's making it go up 3 times as far every single time. Now, how we apply that in this case, well, that's the important part now, right? So, first up, we want to take a look at the asymptote. The asymptote, you notice, if it was just the parent function, my asymptote would be here at 0. But I am stretching it vertically by a factor of 3. So, if I take that line at 0 and I multiply it by 3, where will it be? Still 0. Because, of course, 0 times 3 is still 0. So the asymptote, it didn't move. Just because we are stretching it, it didn't move. It is only going to move, the asymptote, when we have a vertical shift. That is, when you add or subtract something out here at the end. So now we know where our asymptote is. Next up, we always put our first point up 1. Well, not always, as it turns out. It has been always up to this point. But it's no longer going to be always. Because, yes, it normally starts up 1. But, again, I have a vertical stretch by a factor of 3. Well, instead of going up 1, I got to multiply that up by 3. So how far up am I going to be starting? 3. And so our very first point here is no longer at 1. Our first point's at 3. Now, some people will try to shortcut this and they'll think about, okay, well then whatever I multiply by, that's my y-intercept. That is valid most of the time, and it's a decent way to think about it. But you're going to be better served in the long run if you think of it as taking the 1 and multiplying it by 3. It's going to help you not get tripped up in some little subtleties later on, like if I move it sideways, then it's no longer a y-intercept, but it is still multiplying the height by 3, stuff like that. All right, so now that I got that first point, I've used the vertical stretch by a factor of 3, and now that I have that first point plotted, all I have to do is know the parent function. Because the parent function tells me where to go from my first point. Remember, 2 to the x means double your height. Well, my first height here, of course, it's at 3, right? If I double 3, what do I get? We get 6. And so my next point's got to be up 6. Okay, for the next point after that, how high would I need to go? Well, remember, I'm always doubling my last height. So my last height was 6. If I double the 6, I end up getting 12. Now that's going to be off my particular graphing grid. If yours went up to 12, plot that point. I went ahead and kind of sketched it in there just for the moment so you can see that it would be up there. Doesn't mean you got to plot it off your grid. If it doesn't fit on your grid, don't worry about it. So notice the rule ended up being the same. I put in my first point, and then all I had to do was double the height as I went to the right. So 3 became 6. 6 becomes 12. 12 would become 24. 24 times 2 would give me 48 for the next one after that. 48 times 2 after that would be 96, and so on and so forth. We just keep doubling our height. So if I double the height going to the right, what am I doing as I go to the left? It's going down, but it's being cut in half. It's like we're dividing by 2. Now, this is where sometimes it can be a little bit trickier for us, because right now it's at 3, right? If I cut that in half, how high will it be? Half of 3 is 1.5. And so you'll notice it's not down at a half, it's at 1.5, because I'm literally taking the height that I started at and I'm cutting that in half, bringing it down. And then for the next point after that, I'm going to cut that height in half. And so there I'm going to be somewhere in here, it looks like. Somewhere between 0 and 1.5. Technically, that number is actually 3/4. You could calculate it if you want to. But you can also eyeball it as saying, okay, well, it's half of that distance. And we can just keep cutting those distances in half going over to the left. The numbers just aren't quite as easy to think about, for some of us at least, as we go through. And that's okay, because you can still do it just visually. You can just look and see, cut this distance in half, cut this distance in half, etc., etc. Now, once we got our dots plotted, and yes, at least a couple of the ones where you cut them in half, please. You don't necessarily need all of those whenever you make these, but you do need at least a couple. We can go ahead and draw on the curve. So we draw our curve in, we have our graph with our vertical stretch. Last thing we want to look at here, domain and range. What's the domain of this graph? It's an exponential, so yes, it's all real numbers, because it goes forever left and it goes forever right. What about the range? It's not all real numbers. So range is dealing with y values. It's going above the asymptote, so that's going to be greater. Remember, not greater than or equal to, because it doesn't actually hit the asymptote, which is at 0. And so our range then is y is greater than 0. All right, for our next one here, we have 1/2 times 4 to the power of x. All right, want to start off by thinking about transformations, things like that. Well, first of all, our parent function, remember, is whatever the number is to the power of x, so that's my parent. Which means the 1/2 represents a transformation. Now, when we multiplied the last one by 3, it made it bigger. That was a vertical stretch. Multiplying by 1/2 makes it smaller. What do we call it when we make it smaller? It's a vertical what? Compression. Think about if you're squishing something down, you're compressing it. That kind of an idea there. Now, is our asymptote going to still be at 0, or is it going to move here? It is still at 0, yes, because again, there's nothing added or subtracted on the end. So, this is a vertical compression by a factor of 1/2. My asymptote is at 0, so I start by drawing that asymptote in here. And then, having drawn that in, I now need to plot my first point. Now, of course, normally my first point was up 1, but it's not going to be in this case. My vertical compression is changing that. So, the up 1 is going to change to be up how far for my first point? I'm multiplying my height by 1/2. What's 1 times 1/2? It's 1/2. And so we actually are starting at 1/2. It's really tempting at this point to think starts at 2, right? Because it's easier to think about it starting at a 2 than it is starting at a fraction like this. But this is actually just what it's going to be doing. We just have to go based on this number here. Take your normal up 1, multiply it by the stretch or compression. Now that I have my first point, thankfully, we are done with that 1/2 now. I don't have to worry about it anymore. The only other thing I have to be dealing with and thinking about is the fact that this one is 4 to the power of x, meaning I multiply my height by 4. So I just went up 1/2. How far up am I going to go up next? Well, what's 1/2 times 4? 2. So my next point then, it's going to be up 2. And then I just went up 2. How far am I going to go up next? Again, it's 4 to the power of x, so I'm multiplying the height, my last height, by 4. If I just went up 2, 2 times 4 is 8. And so our next point is up 8. So notice here, really, I'm trying to get us focused on the idea of the transformations determine where that first point is, but once you plotted that first point, the only thing that matters is what the number is to the power of x. That is, what is our base? Because 4 to the power of x means multiply the height by 4. Whatever it was, multiply it by 4. Now going to the left, of course, I'd divide by 4. And you'll notice we're going to get into some small numbers really quick here. Because up 1/2, if I cut half and divide it by 4, I end up down at like an 1/8. technically speaking. If I divide that by 4 to go even smaller than that, then we're down at like a 32nd. You're probably not going to plot 1/32 exactly. You're just going to plot something that looks really, really small compared to that last one. 1/4 is high, in other words. But again, we want to plot at least a couple on that side because it's going to help us be able to make that curve nice and smooth and accurate. And so we go ahead and draw that curve in there. Then the one last question we got here, just kind of bringing back some of our vocabulary from before, is this an example of exponential growth or is it exponential decay? Well, we got two ways we can know it. One way is you can always just look at the base, and only the base. It's the only thing that matters. Since I'm multiplying by 4, it's getting bigger. Therefore, it is going to be growth. The other way you could do it, though, is you could look at it and you could say, as I'm headed to the right, is it getting further away from the asymptote, or is it getting closer to the asymptote? When it's getting further away like this, it's growing. We're going to have more of that distance. And so it'd be growing. If it was getting closer, it'd be decay. Now in this case, our parent function is the 1/3 to the power of x. So when you think of your transformations, notice there's two of them in this case. We're multiplying by 6 and we're subtracting 8. Now the subtracting 8, it's at the end, it's not up with x, so that means it's moving it up and down. Specifically, it's going to move it down 8. Multiplying by 6, that's going to be a vertical stretch by a factor of 6. Notice the shifting down 8 is what determines our asymptote. So my asymptote is going to be down at -8. Of course, from there, the most critical step is knowing where does the first point go. Normally, the first point is up 1, yes. In this case, how far up will we go to get to our first point? 6, because I'm multiplying every single height by the 6. Once you plotted that point, all you got to do is know that it's 1/3 to the power of x. So use that the same way that you used it before we did any stretches. And so from there, that height is at 6. As I head to the right, I want to be multiplying my heights by 1/3, or dividing by 3. Same thing, right? So if that first point's at 6, my next point then is going to need to be at a height of 2. Because 1/3 of 6 is 2, or in other words, 6 divided by 3. Then, from there, I have 2. I now want to go to 1/3 of the height of that. Now, 1/3 of the height of that is not at 1/3, it's actually at 2/3. It's a little bit awkward. Go ahead and do it visually if actually thinking of the number 2/3 is throwing you off a little bit. Now, as I headed to the right, I divided by 3. So as I head to the left, I'm going to multiply by 3. So the first point that I plotted, again right here, that was up 6. And again, I'm always thinking about what was that actual distance. The 6 is what I care about there. What's 6 times 3? It's 18. Can I fit that point on here? Is there enough room to go up 18 from my particular asymptote in this problem? Yes. Because I happen to start us down 8, which means that I can go a total of 8. How convenient. And so I plot that point. I'm definitely not going to fit any others on. If I wanted to try to know where the next one would be, I would be having to go up 18 times 3. It'd be way up there. Having plotted those points, go ahead and draw your curve that goes through them. Then last question here, is this exponential growth or is it decay? It is decay, yes. Now how do I know that? Again, two different ways. The fact that my base is less than 1, that tells me decay right there. The other way, visually, I can see that it's getting closer to the asymptote. Anytime it's getting closer to the asymptote, that distance is decreasing, hence decay. Now there is a lot going on in this equation, so now that you've had a chance to think it through a little bit, let's go ahead and check in, make sure that your initial thoughts are heading in the right direction. Our parent function is going to be 3 to the power of x. So we know that once we plot 1 point, I'm going to be tripling. But from there, it's all a matter of where does that first point go. The 2 is a vertical stretch by a factor of 2. The plus 1, it's up with x, therefore it's shifting it left 1. The minus 9, it's hanging on the end, therefore that is shifting down 9. Now since it is shifting it down 9, that also means that the asymptote is going to be at y equals negative 9. And so notice how we list out those transformations. And then when we know those transformations, we know how to make the graph. In fact, I could even not give you the equation at this point, just give you all of this information, and it should be able to make the graph from that. So we're going to start by drawing in our asymptote, but then my first point will be left 1 and up 2. So let's actually see that here. I draw my asymptote down here at negative 9. My first point is normally right here, up 1. But vertical stretch of 2 means instead of starting up 1, I'm going to start up 2. And then shifting it left 1 means that point shifts left 1. So then that's actually my first point. Now that I know where that first point went, I've used my vertical stretch by a factor of 2. I've shifted it left 1. I've shifted it down 9. I don't even need to think about those anymore. All that matters now is the fact that this is 3 to the power of x. So I'm just going to say I got a point here. I'm going to triple its height as I go to the right. So as I head to the right, I am multiplying each height by 3. So the first point was at 2. So the next point then must be up 6. Make sure you're counting from the asymptote when you plot those and count them out. It's not from the first point, it's from the asymptote. It's the actual height. So that one's up 6. I then multiply that by 3. 3 times 6 gave me 18 again. And so that number right there is a total of 18 up from the asymptote. Now headed to the left, I need to be dividing by 3. So my first point here, I'm going to take the 2 and I'm going to divide it by 3. If you're a numbers person, you're going to be saying, okay, that's 2/3. So I'm going to go ahead and plot it at 2/3. If you're not liking that, some of you are much more visual, and that's okay. You're going to take this actual distance right here and visually say, okay, how long is 1/3 of that? Well, 1/3 of it would be about there. So that tells me I can plot my point at that height. And then for my next point, I have to visualize where 1/3 of that is. Now again, you could actually get that as a number. It's 2/9 in case you actually want to. But I think most of us at this point are going to look at that again visually and say, okay, I just have this distance, and I just want to visualize how much is 1/3 of that total distance. And then plot that close as you can. Remember, we can't be necessarily perfect with these, but we can be pretty darn close. Now that we've drawn at least a couple of the points on each side there, we can go ahead and draw on our. Last couple ideas here, the domain and the range. It is exponential, so the domain is all real numbers. The range, it's not all real numbers. It's y. We're above the asymptote, therefore it's greater than, and it is specifically greater than -9. Because it's always relative to the asymptote, because that's either as high or as low as it can possibly go.